Now we will apply the conservation of energy principle to planar kinetics of a rigid body problem. Okay. We recall the principle of conservation of energy. Okay. From this principle, we know that the energy of the system is conserved when a rigid body is acted upon by a system of conservative force. Okay, so the work done by this force is conserved. Okay, so that it means that the sum of kinetic energy and potential energy is remain constant. That is T1 plus V1 equal to T2 plus V2. Okay, and we review for the case of gravitational potential energy. The gravitational potential energy of the body is defined by Vg is equal to the weight times the vertical distance. Okay, and it is positive when it is above the datum. Okay, and it is negative when it's below the datum. For the case of spring, for the spring force, the potential energy of the spring force is always positive, and it is equal to a half kS squared. And S is defined as the deformed length, the deformed length of the spring. Okay. So let's take a look at this example. The rod AB has a mass of 10 kg and the piston B is attached to a spring of constant K equal to 800 Newton per meter. Okay, the spring is unstretched when theta equal to 0 degree, and we will not consider the mass of the piston. Okay, we would like to find the angular velocity of the rod AB when theta equal to 0 degree. If the rod is released from rest when theta equal to 30 degree. Okay, so because or if we consider this system is composed of just only the spring force and the gravity force, so this system is a conservative system. So then we can apply the principle of conservation of energy to this system. We starting with draw the image for we may have to imagine the initial position and the final position. Okay, and we have to starting with set up the data, and now here we set up the data. We set up this line, this key line to become the data now. Okay, and for this case, if we set up the data here, it means that the potential energy at second position at the final position is become 0 now. It's become 0, and then for the gravitational potential energy at first position, it should be negative because it is below the datum. It is equal to mass. This is the mass of the rod times g, that is the gravity constant, times h. H is this distance here from the datum. Okay, as we know that the length of the rod is equal to 0.4 meter. Okay, so this is the angle 30 degree. So then this is become 0.4 sine 30 degree. That is equal to S1 also. That is the deformed length of the spring. Okay. And from this, in order to find this 10 from the datum of the center of mass of the rod H, this is a half of S1. So then we can derive for the potential energy due to gravity first, that is this term. And for the elastic potential energy, it is equal to a half. This is a half Ks1 squared. Okay, this is mgh. And the elastic potential energy due to spring is always positive. We know the spring constant when we know the state length is equal to 0.4 sine 30 degree, okay, square. And then we can find the potential energy at the first position now is equal to 6.19 Newton meter. And for the kinetic energy, because the lot is released from rest, so kinetic energy at the first position is become 0. And for the final position, the kinetic energy is composed of kinetic energy due to translation and rotation, that is a half mvg square and a half I omega square, ig omega square. Okay. So for this case, we would like to find g and omega. And if we consider at the position 2 at point A is the instantaneous center of rotation. So then for this case, we know that Vg is equal to Rg sub Ic omega, that is equal to 0.2 omega 2. So now we can derive T2, that is equal to 0.2 omega 2 squared plus 0.067 omega 2 squared, that is become here. And after we apply the conservation of energy equation, substitute into this equation, we can solve for omega 2, that is equal to 4.82 radian per second. That is not in this direction. Okay, let's complete this problem.